Welcome to my presentation, a new Linux kernel subsystem for JESD204 multi-channel RF Transceiver Systems. My name is Hennerich. I'm Software Engineering Manager and also Linux kernel developer at Analog Devices in the Systems Development Group. On the coming slides, I briefly introduce the JESD204 Standard, the architecture, the components involved, and also the challenges they have. The JESD204 Standard defines a high-speed serial data link between converter, ADCs or DACs, and logic devices with up to 32 lanes per link and lane rates up to 32 gigabits per second. In the standard, you also find the possible data framing and mappings, provisions for multichip synchronization and deterministic latency. So there have been many iterations of the standard. Back in 2006, there were also only one lane with only 3 gigabits per second defined. Later on, they introduced multi-lane capabilities. In 2012, they raised the maximum lane rates to 12.5 gigabits and also added deterministic latency using subclass 1 and 2. In addition, there's also a more flexible clocking scheme defined. The latest iteration of the standard, called JESD204C, was introduced in 2017, which raised the maximum lane rates to 32 gigabits and also had options for more efficient 64B, 66B or 64B, 80B encodings and provisions for forward error correction. Here we see the basic architecture of such a system. We have a transmitter and a receiver. Between the transmitter and the receiver, there are one or multiple high-speed serial lanes. From the receiver back to the transmitter, there is a sync signal, which is only available in 204B modes, which indicates which tells the transmitter that the receiver is ready to receive the code group synchronization sequence. Once successfully received by the receiver deasserts or asserts the sync signal again, and the transmitter starts sending the initial lane alignment sequence followed by the data. There's a third component in here, which is the clock chip, which is quite important as it provides a device clock to both the transmitter and the receiver. And for subclass 1, deterministic latency, there is an additional signal called sysref, which kind of resets the local multi-frame clocks in both the transmitter and the receiver. Strict timing requirements applies to sysref and device clock. If you look at this from an OSI layer point of view, there is a physical layer where we have the high-speed serializer and deserializers, the clock recovery and the signal shaping. On the link layer, we find the scrambling, the character replacement, and the 8B and 10B encoding. On the transport layer, there's sample framing, deframing, lane mappings, and so forth. Let's have a closer look at the individual components. The converter device does either A to D or D to A conversion, sometimes both. It contains one or more synchronous converters. Modern converters, especially in RF transceivers, often include digital processing features just like digital down converters, digital up converters, channelizers, or numerically controlled oscillators. The logic device is often implemented in an FPGA and implements the digital signal processing. One logic device can interface multiple synchronous converter devices. The clock generator is a circuit used to generate synchronous phase-aligned clocks to various devices in the JESD204 system, such as device clocks, link clocks, serializer, deserializer reference clocks, sysref, or even the converter sampling clocks. And this is where a lot of the complexity lies in such a system. We have a reference clock, 2 cascaded PLLs, a fixed VCXO frequency, output dividers for the different clocks. Each of the components, again, have built-in internal PLLs with input dividers, feedback dividers, multiple PLLs. The converter device itself has multiple options, for example, to receive the sampling clock directly or through a PLL. There are reference dividers, and there's also a serializer, deserializer PLL that needs to be capable of generating the required lane rates and so forth. So a lot of complexity is actually making sure that you can generate the required clocks for a certain application. Let's take a closer look at each individual component. The logic device file layer, basically the SerDes or transceivers. There are different vendors, just to mention a few big ones, Xilinx, Intel, Altera. Each of those vendors do have different architecture and generations of their transceivers, GTX, GTH, GTY, for example, at Xilinx. Each of those transceivers do have different PLL blocks, quad PLL, channel PLL, or Intel names them ATX and CDR. Each of these FPGA devices are available in different speed grades, and this goes hand in hand with different VCO bands, frequency ranges, and so forth. So each PLL has its own math and its own constraints. So sometimes you also want to share PLL between links, so there needs to be some resource management. And of course, you want to control the lane rates based on the link parameters or the higher level application settings. Looking at the clock generator, it needs to provide multiple phase aligned clocks for link bring up and maintenance, of course. Lane rate divided by 40 or lane rate divided by 66. Some divide down of the local multi-frame clock, some sampling clocks, and so forth. All these clocks need to go hand in hand with also the file layer PLLs and their capabilities. The clock generator for subclass 1 also needs to be capable to provide like single shot triggers or continuous triggers with a certain frequency. Often you find multi-level clock trees where you basically have a tree of clock trees that are cascaded. Also, all these clock chips do have different VCO bands, output divider constraints. Some devices don't support odd dividers. Some provide odd dividers, but not for all values. Then you have a VCXO frequency that kind of limits also the possible VCO frequencies. And also very important are the phase noise and jitter considerations. So this really calls for a modular software design and device drivers that abstract hardware implementation details. So the challenges on the link and transport layer are that matching link parameters need to be programmed on both sides of the links and also at various components of the link. You see in the next excerpt the most important parameters on the right side of the slide. For example, number of lanes, frames per multi-frame, octets per frame, the converter resolution, or the number of bits per sample, the JESD version, the subclass, whether scrambling is enabled or not. Also, certain modes require an additional gearbox, which causes a more complex clocking. Certain modes might even not be supported by hardware, so you need to manage what is supported and what not, and kind of error out. Then, like I said, there are different versions of the standard, different encodings. For for example, 204B, we need to handle CGS and ILAS via the sync strobe. The sync strobe doesn't exist on 204C, so you need to implement an application layer sync, which is handled in software. There's different encodings, we also require different math on the lane rate computation and so forth. Distributed multi-chip clock synchronization is also often challenging. So the requirements are to deterministically align clocks and minimize channel skews across all outputs and layers in the clocking tree, and also to meet setup and hold times for subsystem signals relative to the device clock at each data converter. The problems are a large number of clocks are required. We need to maintain deterministic phase accuracy across multiple levels of clock expansion, maintain jitter, phase noise performance across all layers, and also we need some mechanics to synchronize multiple device clock trees structures which are not based on a simple clock buffer. So the system looked relatively simple until now, but in fact each component hides hundreds of registers. There are several PLLs and vendor-specific high-speed transceivers which the user needs to program. So this suddenly does not look an easy task to do anymore. And also debugging such a system is difficult, especially since if one component fails, the entire link fails. So the challenge is to mitigate this complexity and allow the end user to manage the system from an application perspective. So what we learned until now that the JESD204 based interface converter systems can be complex. Multiple hardware, HDL, and software components need to gracefully interact. The JESD interface framework that we developed is a system-level integrated HDL and software framework covering the entire stack, from physical, link, transport, and application layer to address exactly those challenges. Some key features include automatic interface configuration based on application settings, dynamic reconfiguration, and improved diagnostics. It's supposed to work out of the box, while it's also a great starting point for customer development. Let's have a look at the scope and requirements for a more integrated software framework. On the top, we see a typical RF transceiver system. We have multiple links. Each of these links have its own file link transport layer. Components, each of these components are device driver instantiations. So we have a total of like 9, 10, 11 devices in here that needs to be handled. They are all instantiated via different buses. For example, the transceiver might be instantiated via the SPI bus, the clock chip via the ASPO-C bus, and the other components via the platform bus. So all of them need to be fully probed before the link can start. Also, the link establishment can be broken down in a sequence of finite steps with all the different link components involved at certain times. Link parameter propagation is also very important because you don't want to set identical parameters at different places. So you want to set them once and they need to be propagated. Error handling and reporting is also a major concern of such a framework. So first of all, we need to be able to see where an error has occurred, and then we need to take appropriate actions. Also, the framework should have provisions to avoid boilerplate code and share code that can be shared across different components. Multi-chip synchronization beyond sub-class 1 deterministic latency for these transceiver systems are often also very important because these RF transceivers do have NCOs, they have RF PLLs that need to be phase synced. And last but not least, we also need a way to describe the links, the flow graph, and the dependencies in a way that doesn't require any hard coding. So it needs to have some sort of description language associated. So all this calls for a new JESD204 Linux kernel framework. Like mentioned before, a link establishment is a sequence of finite steps. Thus, the Linux kernel framework is a finite state machine. Its purpose is to synchronize multiple Linux device drivers to be able to properly bring up and manage a single or multiple JESD204 links. Link bring-up management can be complicated because it requires many actors, device drivers to be in sync with each other in various link bring-up and setup stages. That happens not just at boot time, but also during runtime in case a link is going down or need to be reconfigured, breaks, or needs to be recovered. Typical components of JESD204 links are the file layer, the link layer, the transport layer, the high-speed converter devices with internally also file link and transport layer configurations, the clocking layer, and also the application layer. So the framework needs to manage constraints and all the interdependencies. So on the right, we see such a basic finite state machine where we start in idle state, then move on to state X, and then at some point we get to clock enable, link running, and the last state is the post-running state. So the framework hooks into all the different device drivers that participate in the link management. Each device driver provides a set of callbacks for each state that it supports. The relationship between devices is defined in the device tree. The relation is called a connection, not to reuse the term link, which can cause confusion with the JESD204 standard. The whole group of devices is actually a graph or topology with a single top device. Some design principles. A group of devices shall be named topology or informally graph or tree. Each device driver must register with the framework to be able to take part in the topology. A device may only be part of a topology if it's defined in the device tree via the JESD204 device node definition. Each topology shall have a single top-level device. For multi-chip topologies, one will be picked to be the top-level device. A top-level device may be defined via the JESD204 top device property, where the ID is the number defining the topology ID to be able to specify more than one topology. The top-level device defines the JESD link IDs in the device tree using the JESD204 link IDs array property. The order in this array is the order in which the JESD204 links are also initialized. Let's take a look at the device tree of this example. In yellow, we see the JESD204 device property in all of the components. This is the top level device because it defines the JESD204 top device with ID 0. We also see the JESD204 link IDs, the framer link TX, framer link RX, framer link ORX. These can be just numbers as of 0, 1, and 2. More important here are the JESD input properties. So this RF transceiver device has 3 inputs, the one for each of the links. If you take a look at the framer link TX, this has the P handle of the transport layer core, which is defined here. The transport layer core in return has the P handle of the link layer device. The link layer device in its input has the P handle of the file layer device, And finally, the file layer device has the P handle of the clock device. Let's further look at some more design principles. All devices in a topology must go through the same states together. When bring up a link, and in the same order reverse when bring down the link or rolling back. For example, all devices must go from S0 to S9 together and from S9 to S0 together. When going through each state, each device driver will provide its own set of callbacks of what to do in each state. If a callback is not provided, it's assumed that the device driver doesn't care about that specific state and the transition will automatically continue. When an error occurs in any of the states should automatically be rolled back from the state that has errored back to the initial idle state. Example, going from S0 to S9, S3 false, the transition will be S0, S1, S2, S3, S2, S1, S0 in perfectly symmetry. So rolling back doesn't stop even when any of the states error out, because it's of higher priority to reach back to idle than to stop when rolling back. More principles. Each callback must either return state change done, state change defer, or state change error. The JESD state change defer is important because if a state should stop but not roll back and wait for an external call like a thread or retry mechanism to restart the finite state machine and continue from the current state. So this can be, for example, when transitioning from S0 to S9 and S4 calls for defer, the FSM will stop at state 4 and an external entity like retry loop, work queue, interrupt, etc. would call the FSM to continue the transition up to 9. The defer mechanism logic allows us to pause a transition of states if any device in the topology calls for it because it isn't ready yet. For any particular state, the callbacks of the top level device must be called last. There can only be a single device that can act as a SysRef provider. Too long, didn't read, show me the code. The code of the framework as it is today can be found here. How does it work? A driver needs to provide some data to the framework, basically this init structure. It does that by calling defm JESD204 register with a pointer to that structure. All drivers must finally call the JESD FSM start on their object returned from the framework. This is true for all devices, even the ones that are not the top level devices. There's an equivalent JESD204 FSM stop that will stop the FSM. Proper function of the FSM relies on the drivers correctly using the framework and that the connection between devices are properly defined in the device tree. More about the initialization data on this slide. The SysRef provider can hook itself into the framework using the SysRef provider callback. There is a callback when the FSM finishes a series of transactions, which can be set here. The framework also allows to reserve a certain size of private data structure using the size of private proof. Then you can define the maximum number of links for this device, the number of retries, and of course the state ops. Each driver hooks its callback by adding the proper entry in the state operations array. During a state transition, a state callback will be called either once for each JESD link or once for each device if the mode is set to state ops per device. Optionally, each state may request a sysref call by setting the post state sysref to true. Here are the most important link states in a nutshell. Link init. The JESD204 FSM calls this callback for each JESD204 link defined in the device tree. The top device fills in the struct JESD link, all the parameters for this link. These parameters include the JESD link parameters, the sample rate, the sysref mode, such as continuous or pulsed. In the link supported state, during this state, the FSM core calls for each link of a topology into each device in order to query if it supports this configuration. Whether a configuration is supported or not depends on a number of constraints and synthesis parameters. In case all devices support the configuration, the FSM moves on to the next state. The clock chip drivers, for example, use this state to compute the LMFC, LMEC, LEMC for all the links and find its greatest common denominator so that a common sysref frequency can be computed, which satisfies all the link requirements in the link pre-setup state. So this is typically used by the clock chip drivers to configure the output channels dedicated as sysref and applies the previously computed sysref frequency configuration for the mode. In the link setup state, in this state, all the actors link devices are set up and configured based on the mode and configuration previously validated. A lot of devices typically found in multi-chip setups require additional synchronization steps, such as multi-chip sync, phase NCO sync, or call calibrations, which take a lot of time and would benefit from being done in parallel to save some time. For those cases, opt setup stage 1 to 5 can be used to implement these high-speed converter device-specific configuration, synchronization, and calibration steps. There are some optional clock sync stages. These states can be used by the clock chip drivers to implement a clock tree synchronization mechanism. This is typically device-specific or might not be supported by the clock chip in question. Right now, there are 3 states reserved for this. Based on the example here, this is what happens in each state. In the first state, the sync provider and consumers are configured to generate and receive synchronization requests. In the second state, the synchronization request is issued at the topmost device in the clock tree. In the final state, the sync status of each clock device is validated. Clocks enable, link enable. Depending on the direction of the JESD link, different link components may implement different things. However, as the name implies, it's about enabling the JESD link. This includes taking the link layer cores out of reset, enabling the sysref receivers for subclass 1 operation, requesting sysref pulses, etc. Finally, link running. In this state, all the links of a topology are assumed running. This is typically being checked in this state. Drivers can also use this state to complete setup and configuration, which is required after the JESD links are running. In case another state is required, drivers can also implement the optional opt post-running state for these purposes. Here we see an example of a multi-chip setup. It's taken from the ADRE 9009 Z011EG system on module with an additional FMCOMS8 FMC board connected. In this setup, there are a total of 4 RF transceivers with a 2-level clock tree. The JESD FSM topology and the input connections can be found below. Here we see 2 additional clock chips for the 2-level clock tree and 3 additional converter devices, which are really easily just added in the inputs. These are some boot messages emitted by the framework early during boot, where it kind of lists all the devices, their connections, and it checks for completeness of the topology. So here we found 14 devices in one topology. Later on, once all the devices are probed, here we see the probe messages of the file layer. It says it has 8 lanes, CPLL on GT84. Then here we see the messages from the link layer cores, the 3 of them with the encoding with a number of lanes. And finally, we see the transport layer cores being registered. So that means all the devices are complete, are all probed, and the FSM can start. These are the state transitions from the FSM. At some point, we see some informational or warnings. Later on, this is emitted by the RF transceiver drivers, and finally, we reach the post-running state where we are done. Debuggability and advanced diagnostic was a big topic for the entire framework. So we offer statistical I-scan bit error rate monitoring that allows you to detect electrical signal integrity issues. Clock rate monitoring for all system clocks, detect bad clock wirings or clock failures. There's initial lane sequence monitoring and verification, allows you to detect lane swaps, lane arrival monitoring relative to sysref, to detect potential sources of non-deterministic latency, sysref alignment monitoring, and continuous monitoring. There are different tools. Some of them are GTK based, some of them are in curses and can be run from the console. So the next steps are cleanly to mainline and upstream the entire framework. However, there are a few things that we want to get done first, which are summarized on this slide. Finally, a few words about the JESD framework configuration tool. Travis Collins is going to have a talk about that tool as well. It's configuration tuning for the JESD interface framework and clock infrastructure. It manages converters, serious data path and clock requirements, FPGA transceiver clocking requirements, and clock chip constraints and references. It does so by leveraging nonlinear solvers to quickly solve, validate, and optimize configuration across the entire system. It has a Python library with a command line interface and also some GUIs. It can generate device trees and HDL constraints and also configuration structure for the bare metal drivers. The whole thing is you can use this configuration tool to actually validate configuration, application specific configuration before you order an FPGA board or before you make some component selections on clock chips, VCXO frequencies, and so forth, as it will definitely tell you whether you can use this FPGA in this speed grade or whether you can use this VCXO frequency and so forth. So it's a great tool to validate things before you actually implementing it. So some of the conclusions. The JESD kernel framework greatly simplifies 204 converter systems. Porting new devices to the framework is a straightforward exercise. Of course, it's free and open source software. Some references here, some pointers and links. And finally, let's open up for questions.